All right, so for a question like this, we have a graph of velocity against time, and we want to be sure that we can read sort of what does each division on each axis represent, because we're sort of extracting some data points. And so if we go from 20 to 30, and there's 10 divisions between them, that's, pretty straightforward. Each one is 1. So 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So this is an initial velocity of 22 meters per second. And then at 1 second, we can see that the velocity uniformly decreases, right? So there's a uniform deceleration, change in velocity. And then at 4 seconds, it's going at a speed of, it looks like this is 10, so that would be 8. Okay. And so let's sort of label all this clearly. The initial velocity, we use the letter U for that, 22 meters per second. The final velocity, V, 8 meters per second. All right. And if we wanted to calculate the deceleration, we take the slope, right? So we could kind of consider, this point, this point. But they're actually asking us to solve for the displacement. How far does the car travel while the brakes are applied? And so what we need to do is really consider the area here. All right. So what's the area of that shape? All right. The area of a trapezoid is like 1/2 the sum of the bases times the height. So if you could use like the formula for the area of a trapezoid, I think that's the shape that we've got here. But it's easy enough to do what we did in the derivation of the equations, which is break the motion down into like a rectangle and a triangle. And so here I've got the displacement S equals length times width. And so like the length we could say is 8 meters per second. And then the width goes from 1 to 4 seconds. And so 3 seconds of delta t, right? And so this is just distance equals velocity times time. Okay. Here we have sort of like the decelerated sort of piece of this. And so this is the area of a triangle. And so it solves for displacement. Remember, if we take the area, so the area of a triangle is 1/2 base times height. Now the base is going to be the difference in these velocities, right? So it's going to be u minus v. And so 22 minus 8, 14. 1/2 base times the height is still 3 seconds. Remember, this was meters per second. So meters per second times seconds cancels. I'm left with meters of displacement here. Same thing here, meters per second times seconds. The seconds cancels. I'm left with meters of displacement here. So 8 times 4 is 24 meters from the rectangular part. Yeah, 8 times 3 is 24, right? I think I said it right, but I mean, I said it wrong, but wrote it right. So thank you for catching my mistake. And then we got 14 times 3 divided by 2 or times 1/2, that's 21. So there's only like a couple of students in class first block, because I think of the PSAT testing. And that's why I was like, man, no one caught the error there. I had like the negative sign, transferred it over. So I do appreciate it when students are, looking over the work there. So if I make a mistake and say, wait a minute, where did that come from? It's like, oh, thank you for catching it. That almost cost me the job. 24 plus 21, 45. So choice B. All right, so we add these two, right? Because there's some displacement from this part of it, some displacement from this part of it. So while the brakes are applied, would have covered 45 total meters of ground. Any questions on that one? Well, let's keep a good thing going then. And consider this question. A stone is thrown horizontally from the top of a cliff and falls into the sea sometime later. Air resistance is negligible. Which graph shows how the vertical component v sub v of velocity of this stone varies with its horizontal component v sub h of velocity as it moves through the air. Now, this is a good sample paper 1 question as we consider reviewing for the midterm, because it's sort of related. I mean, it is related to the learning objective. If you said, what learning objective is this related to? Explain projectile motion in terms of horizontal and vertical components of motion. And yet it's still somewhat unfamiliar. You really have to think your way through it. Like, what makes sense up there? We're looking, how does one vary against the other one? Not how does it vary with time, right? Or position, but like, how does one velocity vary against the other one? So I'll give you all a couple of moments to discuss this with your neighbors. If you're watching this on YouTube, then you take a couple of moments right now to consider what you think is the answer before I go through the explanation here and see if your thinking doesn't sort of match. Yep, feel free to sort of get together in a group of your colleagues there, see if they've got any thoughts on it. See if you can't talk it out. Sometimes we just sort of talk our way through it, and that allows us to sort of get to the answer. So it's 10:57, and at 10:59, in 2 minutes, we're going to go over it. It's 10:58 now.
Between A and B, actually, no, it's gotta be A because at a certain point, the vertical velocity, the x velocity, is going to stop and it's just going to keep accelerating in the y because of gravity. So,
All right, the time is now 10:59 a.m. I'm interested to hear what are the students' thoughts on this question. And again, you don't want to take too much time with any one question. They're all worth the same amount. If you're really racking your brain over something, like pick your best guess and then kind of move on, star it, come back to it. You don't want to spend, 85 minutes on question 7 at the expense of never getting to questions 8 through 22, or however many questions are on the midterm. So what would you pick as your answer here, even if you had to guess? Who's brave enough to offer their best guess or their best educated guess? Yeah. A is incorrect.
B.
Krista. Say it again. D? I can't hear you. B 2? If A is 1, B is 2. B is incorrect. What? But did anyone think C? Because I want to shoot them down too. Nope, C is incorrect. Yes, D, because that way we kind of get everybody, So, and if you can sort of think about what the physics is here, let's try to prove to ourselves and everybody here that's like, wait, why isn't it A, B, or C? I thought it was that. Like let's look at D together here and like solidify this in our mind that of course that's the correct answer. And now I'll never get another one like that wrong again. What do we know about the horizontal component of velocity for a projectile? It is constant. It does not change. And so this one just stays a constant value here. But what's happening to the vertical component as it's falling, right? We throw it horizontally, and that never changes because there's no wind resistance. It stays the same x component all throughout. And so that's just like this value right here. Let's say we threw it at 5 meters per second. So it stays at 5, doesn't change, it doesn't vary, all right? But what happens to the vertical component? The moment we release it from the top of our cliff, in the y direction, it's going 0. But then what does gravity do? 1 second later, it speeds it up to 9.8 meters per second, right? Because that's the acceleration. Every second, it gains this much velocity. So let's say 1 second later, it's got that velocity because it uniformly increased, right? At every sort of step along the way. And so D is correct here. Sometimes students, we shy away from a vertical line because like, that's undefined. That's, you know, nothing in math. But remember, we're relating one quantity against the other one, okay? So it's like, how does this change with this? Well, with the constant v sub h, with the constant x component of velocity, the y component just increases. And so that agrees with sort of choice D. Now, hopefully, sort of just by thinking through it like that, you say, oh, okay, yeah, that makes sense now. I see why D is the right answer. Is anybody still kind of confused on that? Or maybe there's another way we need to explain it. Sometimes students can explain it to their colleagues better than I can. And it's like, once a student sort of gets the idea, it's like, oh, think about it like this, you know? And then we all want to kind of make sure that we're mastering these learning objectives. You know, like we know we can maybe like put an equation down, we can sort of puzzle our way through it, calculate. You really have to know the concepts. Mathematics is a powerful way to think. It's a useful skill to have at your disposal in science. But the best scientists are not the best mathematicians, okay? They're sort of the most creative thinkers. They're the people that can really kind of think through a concept. You know, Einstein was a really good mathematician, but he wasn't like the best, okay? He wasn't, you know, if you had a list, I always say if you put a list of the 10 best mathematicians in the history of humankind, Einstein would not be on that list. You know, arguably, some people might make an argument. But if you put a list of the best physicists, he's right at the top of the list, in my opinion, okay? So you don't have to be the best mathematician to be the best physicist because the concepts are so important to make sense of. What about a mass on the end of a spring bounces up and down as shown after being released at time t equals 0? So they're giving us like a distance versus time plot. This thing is down and then it goes up through equilibrium and then it goes up and then it goes down and so on. A spring bouncing up and down. We've seen that before. Spring mass system, right? But now we're trying to get a corresponding velocity time plot. And so being able to take a displacement time graph, that's what we did yesterday, right? Drawing and interpreting displacement time graphs. And now we're saying, what's the corresponding velocity time plot that sort of represents that? All right, and I've only given you the first 3 choices up there because I already had to kind of make it smaller so that even these would fit. And so D is incorrect, I'll just tell you that. Like one of the right answers is already up there. It is a, you know, multiple choice out of 4. I'll just show you what D looks like. So D is this thing down here that's like doesn't go down below the x-axis. All right.
If you've taken calculus, you immediately know the answer to this.
Okay, so people with calculus are allowed to use it. You don't have to say this is an algebra-based physics course. No calculus allowed. Leave it at the door. You're allowed to use calculus if you know it. Okay, so you're saying, oh, the first time derivative of that displacement is velocity. I know how to take a derivative of something that looks like that. Is that what you're thinking?
Yeah.
Feel free to think that way. I don't think about it like that because I'm not a very sort of natural mathematical thinker. Okay, so I don't, you know, I tutor students like every evening after I leave here, I go home and typically the students that I tutor are teachers that are like elementary school teachers that have to pass like their math tests and they're like English majors. And so they're like, they forgot all their math. And so I teach, you know, like basically adult learners mathematics. And sometimes these teachers think, oh, we need to turn this into an equation. And I'm like, well, yeah, I mean, if you know how to do that, can you turn this into an equation? And sometimes you have to, like you have to turn a word problem into an equation, but other times, you know, maybe you don't need to, maybe you can just kind of think through it logically. And so I remember having a conversation with, you know, one of my students, you know, that sort of suggested that, hey, we could write an equation out of this. And I'm like, I don't know how to, you know, like, and I do a lot of math, you know, in sort of my everyday thinking. So I would kind of just think through it like this. At its maximum distance down, what's its velocity? That's when it's reached all the way at the bottom of the spring and the spring is sort of stretched out maximum and then it's going to turn it around and go back up. So like when it's at maximum displacement down, its velocity is 0. And so I could eliminate choice B right off the bat and say, well, the velocity up here is positive and I know it's got to start at 0. So it's either got to be like of the choices given here, A or C. And then I think about as it goes through its equilibrium position, this is where it's like converted all of that elastic potential energy into maximum kinetic energy, right? We convert that elastic into kinetic, and then the spring has to sort of compress again, right? And so its maximum distance up, it also reaches a speed of 0 by like this time. And so I'm looking for the graph where it's like, okay, it's at a speed of 0 again up here. That's this one is not. This one is at a speed of 0 again. So I have to kind of consider, what's the correct sort of thing happening with this? It's reached top velocity going up as it passes through this point. Okay, as it passes through this point right here, this time, it's moving up with maximum velocity. And so that corresponds with this point right here, right? Like this is the maximum velocity going up at the time that would suggest that it is that. And so just by considering really this point and this point, you can kind of prove that A is the correct answer. It matches sort of what we would expect by just thinking about this is a spring, this is a real object, right? A spring that's in front of me in the lab, and I can observe it, sort of at rest, that's moving up really, really fast through equilibrium. And this is like the equilibrium position is like before I've pulled it down and let it start bouncing, it just sits there, right? That's its equilibrium position. So when I pull it down, it's not moving, I let go of it. As it passes back through that point that it originally was like resting at, that's where it's going fastest. Because as it goes up here, the spring is compressing, right? And that spring always has that restoring force that wants to push back the other way. You stretch the spring out because I pull it down, it wants to pull back up. That's why it moves up when I let go of it. As it moves through equilibrium, it compresses, right? And now the spring is being compressed and it wants to sort of push back, which is why once it gets to maximum compression, maximum distance up, it pushes back down, and that's why it oscillates, right? The spring is sort of a restoring force there. And so A is the correct answer to this. Maybe one more. The graph shows the variation of velocity v with time t for an object. The object passes a fixed point at time t equals 0. What is the displacement of the object from the fixed point at time t equals 5? And what is the acceleration of the object? Isn't that such a nice one for review? It's like velocity time graph, a chance to take the slope and the area underneath. There we go. I'll give you a head start, and then we'll compare notes in a moment here. Okay, I showed on the figure there where that equation of motion comes from. It's the same. If you said, I need to take the area underneath that curve, you got to take the area of this rectangular part of the graph. Well, that's this part of this equation, right? The constant velocity u that we started with times the time t. So the 20 meters of ground we covered, we would have covered even if we didn't accelerate, right? If we just stayed at 4, we would have covered 20 meters just by going that fast for 5 seconds. But we get an additional 50 meters because we sped up from 4 to 24 over the same 5 seconds. And so this 1/2 AT squared area is this. And because we already calculated the acceleration, you know, final velocity 24 minus initial velocity 4 over the time difference of 5, that's 4 meters per second squared. I can just plug that in for acceleration, 5 seconds squared to get that 70. So the area of this part of it is 50 meters, and the area of this part is 20 meters. The sum of them, that's the plus sign, right? 20 plus half of 100 is 50, is 70 total meters. And so choice B is correct for this one. And you can kind of see like this is the derivation of these equations comes from considering a graph like this. And so I try to sort of, you know, show that you could either think about it as geometry. I'm taking an area of a triangle, of a rectangle. You're familiar with that. You can add them. Or you could think about it more like physics class, like, hey, I've got all these equations of motion at my disposal. Let me just sort of extract the relevant data from that and plug it in. It is one and the same. They're the same way of thinking. Well, different ways of thinking, but sort of identical. Now, we could do question 8, but the through the air part of it, okay, this is a skydiver, jumps from an aeroplane and falls vertically through the air, which graph shows the variation with time t of the skydiver's vertical velocity v. This is not kinematics, right? That question 8, well, it seems like, hey, velocity time graph, right? This is really more about dynamics and forces. And the clue that you get is this, through the air. That's the only clue that they sort of give you, that, hey, here's something where we need to consider the drag force, the force of drag as a skydiver crashes through air. If we think about this purely kinematically and we say, okay, the skydiver is going to accelerate with gravity, then we would expect A, you know, it's just going to go up like this. But this is not a kinematics question where we don't care about forces. You know, or the only force is gravity, right? And we just say, okay, there's the acceleration due to gravity. That's what would happen. That's what happens initially to the skydiver. But then the drag force starts to equal the weight, and then eventually they are exactly equal. And at that point, the skydiver has reached terminal velocity, right? And so this is the plot that we recognize as something that starts out under the acceleration due to gravity, but then something happens, another force sort of starts to counteract it until they become equal. Because the drag force is proportional to velocity, as we pick up speed, that force gets bigger and bigger and bigger until it's eventually going to equal the weight, right? The weight down is what causes the initial acceleration, force due to gravity. And so we have to kind of think about, again, the concepts here. Through the air is a clue that we care about the drag force, right? The force of something crashing through air, and that's going to mean that C is the correct answer to this. This is the one that correctly shows the skydiver's vertical velocity. But we'll save that for tomorrow, okay, where we go over dynamics and all the learning objectives sort of belonging to that one, okay? You still have about 30 minutes left in class to let your brain recover. You know, it's a lot of physics, okay? And then this is just chapter 2. So tomorrow, chapter 3, Friday, chapter 4, Monday, chapter 5, Tuesday, chapter 6, Wednesday, chapter 7, Thursday, exam, midterm. You guys take the midterm on Thursday in this class? Take it Friday.
I have no idea.
Let's cue that up.
Oh wait, no, Thursdays. Yeah, Thursday.
I think I've reminded myself like 15 times and I still can't remember.
It's 2.
Hold on, let me be mindful not to maybe like publish all my emails. All the emails, you know, public record.
I see the ones that I still don't wait, so the second, 14th, first. He's like making a test.
Yeah, Thursday. Thursday is your guys' exam, October 22nd. And at the regularly scheduled class time. So you'll go to first period, but you won't take an exam, but then you'll come here and that's your first exam. So like your first exam of the midterm season is this one. Then later on that afternoon, you'll take your fourth period exam, 2 o'clock. And then on Friday, that's when it's an early release day. And so the your first period exam will be, first period, but then you come here and we'll just kind of, I don't know what we'll do. We are going to meet on Friday, but we'll have already taken the exam or the midterm. So we could start like chapter 8, I guess. We'll start chapter 8 on Friday, or maybe we'll just, do something else. I haven't really decided. And then you go to fourth period, and then you go to third period for your exam there at the end of the day. I got to remember to request that afternoon off. Let me do that. All right, anybody need that exam schedule for a moment or two longer, either next Thursday or Friday? I'm gonna put this all on one page. I did in fifth period last year, in AICE Physics last year, we went out and did it. And then when I came back in at the beginning of this school year, the gourds were decomposed beyond sort of any kind of recognition. And hey, we are getting back into pumpkin season here, so yeah, last year there were some gourds donated by a local pumpkin patch, and we did indeed launch them. All right, as is mentioned in the week 8 midterm review, don't forget about your lab work, okay? Practice answering previous paper 1 questions, the first 20 to 22 questions of any paper 1, or you can go on to the midterm review. Some of the questions that we just did were actually in that midterm review, so we did a couple of them together.